Well, it's really only in Minnesota that you can go from what's kind of a hot September 30th, right? It's going to be like 83 degrees today. Did you hear that? 83 and muggy out. It's going to be hot. And then tomorrow it's going to be like 55 and rainy and windy. A blustery day tomorrow. So it's only in Minnesota that that can happen. It seems like you can go from hot to cold and right back to hot again. It's pretty cold yesterday too, wasn't it? I think so. Anyway, we have exam week this week. Lecture 10 today, we'll talk about the last bit of main content to know for the exam. And then on Wednesday, we will review for the exam to help you start thinking about it. But you should also start thinking about it as you work on your homework due on Wednesday. There will be a completion assignment, though I don't think I quite have it up yet. I'll get it up this afternoon. A lot to do. Lecture 10a, I'm going to talk about a couple rational function applications. We'll look again at the limit definition, continuity, and discontinuity. Lecture 10b, I'm sure we'll talk more about limits and continuity, and then we'll talk about the derivative as well. We have discussed the derivative already about a week and a half or 2 weeks ago, but now we'll get into more detail about that. Inverse proportionalities is one situation where rational functions come up in applications. And we'll go back to that relatively simple example that we had from the first lecture where we talked about distance equals rate times time. Okay. Now I talked about the fact that distance is proportional to rate and it's also proportional to time. So for example, if you're going 50 miles an hour, well, if you're going 30 miles an hour in a car and you double your speed to 60 miles an hour, you go twice the distance in the same amount of time. Double the speed, you double the distance. Distance is proportional to rate. It's also proportional to time. If you're going at a constant speed of 60 miles an hour and you double the amount of time of travel, then you double the distance as well. If you are going 60 miles an hour and you travel for 1 hour, you go 60 miles. If you travel for 2 hours, you double that to 120 miles. But this also means that rate and time are inversely proportional. Rate is distance divided by time, and likewise, time is distance divided by rate. Probably a little bit more used to using this equation right here. You know you've got to go 120 miles. You want to go there in 2 hours. How fast should you go? 120 miles divided by 2 hours is 60 miles an hour. This one's used fairly often too, though. You want to go 120 miles, and you're going 60 miles an hour. 120 divided by 60 is 2 hours is how long it will take you. Okay? This is a representation of inverse proportionality where the dependent variable is something divided by the independent variable. Which one's dependent and which one is independent? It depends on how you're thinking about it. What's the application? They also, because of that, generate rational functions. So for example, again, for a fixed distance of 120 miles in time in hours, the rate that you need to go to travel 120 miles in t hours is given by this function. R equals 120 over t. So for example, if you would like to go that 120 miles in 2 hours, you need to figure out the rate by using this function. Go to t equals 2, go up to the graph, and you go over to r equals 60 miles per hour. If you want to travel 120 miles in 1 hour, go to t equals 1, go up to the graph, and you have to go 120 miles an hour. Yikes, a little bit too fast. If you want to go 120 miles in half an hour, t equals 0.5, go up to the graph, and you have to go 240 miles an hour. Now we're talking small airplane. If you want to go 120 miles in 0.25 hours, 15 minutes, go to t equals 0.25 and up to the graph, and you get a 480. You have to go 480 miles an hour. That's more of a commercial airline. But I can solve that equation for t in terms of r as well, and get what's really the same graph, but it's on a different scale. And it's telling you something different. Now you want to know the time to travel 120 miles if that's your speed, if you're going r miles an hour. So if you travel 120 miles an hour, it will take you 1 hour. If you travel at 60 miles an hour, right about there, it will take you 2 hours. If you travel at 240 miles an hour, right there, it'll take you half an hour. Both really are actually the exact same graph, just on different scales, and with the axes labeled differently. This function really is its own inverse. That's why I use the inverse function notation. So that's an example of a basic kind of use of rational functions. This is the most basic kind of way they come up in science. Okay? Here's another application. Remember we talked a week or two ago about yield rate of a bond? What was a bond again? That was an investment. It was lecture 6, this is lecture 10. You purchase a bond for $1,020 at time 0. I'll draw that number line again. So this is, I'll call it inflow and outflow. Money flowing in versus money flowing out. The outflow is money flowing out from you to this company or government entity. That's your investment, actually. That's $1,020 at time 0. But then you get money back. It is an investment. You better get some inflow. There's a $50 coupon payment at time 1. And then there's also a $50 coupon payment plus a redemption value of $1,000 at time 0. You get $1,050 at time 2, excuse me, not time 0. Okay? So net-wise, you're getting you're investing $1,020 and you're getting a return really of $1,070. But to find out what kind of interest rate you're getting, what kind of rate of return requires you to adjust for the fact that these amounts are at different times. And I said it's related to the idea of compound interest in the compound interest formula. And you can solve for that unknown rate of return by equating future values, for example. This expression on the left-hand side takes this $1,020 at time 0 and pushes it forward to its future value at time 2. That's why I have 1 plus r squared here. That's your investment, that's the outflow. This is the future values of the inflows back to you. You've got the $1,050 at time 2. It's already an amount of money at time 2, so you do not need to push it further into the future. We're talking about future value at time 2 here. This 50 times 1 plus r is taking this amount and finding its future value 1 year in the future. That's why I raise it to the first power instead of squaring it. That's a quadratic equation in R. We solved that for R back in lecture 6. I'm not going to actually, we used the quadratic formula before. I'm not going to do that today. We're just going to look at a graph of this to see how the answer can be interpreted graphically. There's no rational functions there. However, if we instead equate present values, we figure out how much these quantities are worth at time 0, then we get rational functions. The 1,020 is already occurring in time 0. We do not need to pull that back into the past. Time 0. Time 0 is now, though. We don't need to take these amounts that are in the future. We will need to take these amounts that are in the future and pull them back to the present. But this amount is already in the present. So it's just by itself. But these other amounts, 50 and the 1,050, need to come back to time 0. We need to find their present values. We divide the 50 by 1 plus r because that's coming back by 1 year. And the 1,050 we divide by 1 plus r squared because that's coming back by 2 years. It's still compound interest, just thinking about it in a different way. These equations are really equivalent. I can get from this one to this one by dividing both sides by 1 plus r squared. That's equivalent to this equation. We can solve that for r. And the point I'm making is this is a rational function. They should have the same solutions, and they do. This one's technically easier to solve because we can use the quadratic formula. So if you were going to start with this equation, and you're going to solve it by hand, you'd actually want to convert it back to this equation and then use the quadratic formula like we did in lecture 6. But now I want to solve it graphically. Let's look at the graphs of these things. The future value related function is this one. That was the thing that we set equal to 0. I'd like to find the root of it. We can do it graphically. There it is. And that root is about 0.0394. Okay, if you graph this quadratic function, when r is close to 0, it crosses the r-axis at a small positive number that's about 0.0394, representing 3.94%. That is your approximate yield. As a quadratic, its graph is really a parabola, and it does continue over here and go back up again because it is a parabola. But we don't really care about that part of the graph. We're only interested in a positive yield rate. This is the positive solution to this equation, or to this function. It's its root. And that's what we're after. That's going to be the yield rate. We can do it with the present value related function where we have a rational function. There's this formula. We're setting that equal to 0 and solving for r. We're trying to find the root of this equation. It's very similar. The root occurs at the exact same spot. The graph looks different because it's a different function. It's a rational function. It actually has a, you can see from the formula here, we have vertical asymptote r equals -1. But we don't need to worry about that. We only care about where it crosses the r-axis when r is positive. And it's this exact same value. So on a test, you should be able to think about this with your calculator help. You should be able to make the graph and approximate the root with your calculator. So that's something to practice outside of class sometime this week before the exam. Go ahead, for example, plug this function into your calculator, graph it, try to find the root finding feature, use the root finding feature of your calculator to approximate the root. And again, the moral of the story is when you've got investments, you want bigger yield rates, right? That's going to be a better rate of return for you. A 5% yield rate, for example, is better than a 3.94%. That's the practical need. Okay.
So I think you mentioned this earlier, but for the 102 times 1 plus r squared, is the 1 plus r squared because there's two different points where you get $50, or is it for another reason?
You're talking about like right here? The 1 plus r squared is there because that's what we're thinking about future values. This $1,020 is a payment you're making at time 0. Essentially, we need to use the compound interest formula to find its value 2 years in the future. I'm using the compound interest formula. This one right here, with n equal to 1, I'm just taking that to be the case, thinking of it as being compounded once per year. And t equal to the amount of time, in this case 2 years. P was called the principal in this equation, but I can also solve this equation for p as a function of t as well. I can divide both sides by 1 plus r over n to the nt power like this. And now I can think of the p as representing present value. The value of a future payment at time 0 divided by 1 plus r over n power. And again, in our application, p equals 1. That's why I divide. Okay. All right, back to limits. Again, we started with this intuitive definition of a limit, intuitive description. What does it mean for this equality to be true? Okay. Intuitively, you'd like to make the outputs of the function as close as you like to the value of L by making the inputs close enough to C. Here was an intuitive description. This limit will be true if we can make the outputs f of x as close as we like to L by taking the inputs sufficiently close to C. Regardless of what happens to the function f of x when x equals C. The function might not even be defined at C. It could be a hole in the graph. And again, that's important. We'll see that's important today. Here's the precise, rigorous definition. This one's not precise, because what does close mean? What does close as we like mean? What does sufficiently close mean? Those are vague words. Okay? We need to make it precise, and here is the precise definition. You're not going to have a proof where you have to use this on the exam. I did that for the graded assignment just to give you a little taste of it. I'm not going to put a proof where you use it on the exam. I would like you to understand it intuitively. Let me go ahead and draw a picture again. And then we'll use Mathematica to help us understand it intuitively as well. So you got some number c that's in the domain of your function. And your function, let's go ahead and pretend it's got a removable discontinuity in c. Say it's got a hole in the graph in c. Say it looks like this. Let's go ahead and define it to be something in c, but not to fill in the hole, something strange like that. I claim the limit of a graph like this should still be the second coordinate of the missing point. That should still be known. Epsilon, this Greek letter right here, that is your measure of arbitrary closeness, can be thought of as a vertical distance away from L on the vertical axis. This other number, delta, is something you need to pick sufficiently small so that this happens. Now, in the picture, what does that mean delta should be? These two numbers here and here are the numbers whose outputs are L minus epsilon and L plus epsilon. So as long as I pick delta to be something smaller than the distance between both of those numbers and c, it should work. For example, I can pick delta to be this distance right here. Delta there. This would be c plus delta right here, and this would be c minus delta over here. If I, in this picture, choose delta in this way, then this last line will be true. Remember that the absolute value of a difference is the distance between them. As long as the distance between x and c is less than delta, and not 0 because we don't want x to actually equal c here, then the distance between the output, f of x, and the number L will be less than epsilon. I'll be between L minus epsilon and L plus epsilon. In this picture, that is true. You pick any number in here except c. Don't pick c because the function value there is further away from L. Pick anything in here except c for x. The output of the function at that value of x will be close to L. It will be within epsilon of L. And if you can do this, no matter how small epsilon is, that's what guarantees that the limit of this function is L, in spite of the fact that f of c is something different. The limit as x approaches c of f of x for this function is L. That doesn't equal f of c, but it doesn't have to. The fact that it doesn't equal f of c means this function is not continuous in c. But as far as the limit definition, this is still true. Here's a Mathematica animation of this that I made. So this is the function x squared right here. I chose c to be 1, and that means L is 1 as well. This vertical distance between the green and red line is epsilon. This horizontal distance between the green line and the blue line on either side is delta. But with this particular picture, delta is too big. There are values within delta of 1 whose outputs are further away than epsilon from 1 on the y-axis. However, I can choose delta to be small. Just make delta smaller. Once it's about that small, then the condition holds. For any x in here, the outputs will be within epsilon of L equals 1. If I go ahead and make epsilon smaller, then that small delta that I just picked doesn't work anymore, so I need to pick it even smaller. But I can always do it, because the limit truly is 1 as x approaches 1. Here's another example. This is the example 1 over x. Even for this example, you can choose a sufficiently small delta so that the inputs are within delta of 1 within the blue line, the outputs will be within the red lines. no matter how small epsilon is. I can make delta even smaller so that it works. Okay? You should not be surprised if you find this difficult, okay? Pretty much everybody does. Again, I said last week that Newton and Leibniz didn't even know this stuff. Okay? They lived in the 1600s, early 1700s. They didn't have a rigorous definition, yet they did calculus fine. So why did somebody come up with this definition later on? They did in the 1800s, mid-1800s. It's because there were some anomalies occurring, some mathematical anomalies, difficulties that people didn't anticipate. In particular, especially related to something called Fourier series. Fourier, it's French. Fourier series, especially with regard to that particular subject, which is fundamental to to life in the 21st century here. Fourier series was discovered a couple hundred years ago. It's fundamental to modern day communications, cell phones, for example. Okay? Any kind of signal analysis you need to do uses Fourier series. And the anomalies that were occurring within that subject required people to come up with a true definition of what a limit really is. Okay? It necessitated that. People didn't really understand limits fully before that. A precise definition helps you understand it once you understand the definition. This is related to continuity. This time, with continuity, the function does need to be defined at C. We say f is continuous at C if this equation is true. The limit of the function as x approaches C equals the function value in C. X. Okay? So continuity is actually related to limits. There's no holes in the graph. The holes are filled in. There's also no jump discontinuities. When your function is continuous at C. The graph does not jump like this. The left and right hand limits exist for this kind of situation, but they don't equal each other. So the two-sided limit doesn't exist. If C happens to be an endpoint of the domain of f, then an appropriate one-sided limit can just be considered. For example, with the square root function. The graph looks like that. C equals 0 is an endpoint of the domain. But it's still continuous at 0 because the limit as x approaches 0 from the right still equals f of 0, which is 0. So that's the appropriate one-sided limit in that situation. Then you say f is continuous on a certain subset S of its domain if it is continuous at every point. So the first bullet here is continuity at a point, x equals c. By the way, sometimes you use the word point for a literal point in the plane. Sometimes you use the word point for a number. So don't let that confuse you. I'm doing that when I just said what I said a minute ago. C is a number, but I might also call it a point. Here I'm thinking of it as being a point. So what ways can a function fail to be continuous at C? There's sort of three main ways people think about this. For one thing, the most basic is f might not be defined at C. F of C may not exist. Like with rational functions at their asymptotes. The most basic of which is f of x equals 1 over x. Right? That's not even defined at 0, so it can't be continuous at 0. Even more, there's no way to define it at 0 to make it continuous, because it's got a vertical asymptote. The graph looks like that. But the graph could just have, it could have a jump discontinuity as well. and maybe not be defined at either point. Or it could just have a plain old hole in the graph like that. A second way a function can fail to be continuous at C if it's defined at C, but the limit at C does not exist. Jump discontinuities are like that. The one-sided limits exist, but they're not equal to each other. So the two-sided limit does not exist. The two-sided limit has to equal both one-sided limits. They have to equal each other for the two-sided limit to exist. Finally, another way is that f could be defined as C and its limit could exist, but not equal to function value. That's where you have a hole in the graph and the function is defined for some strange reason to equal something else at C. That's this kind of situation. Reason number two of why a function can fail to be continuous at C can happen in a variety of ways. There could be a jump discontinuity. There could be a vertical asymptote with the function defined at x equals 0 anyway. So for example, this one here, I could say f of x is 1 over x if x is non-zero, and something else if x is 0, or if x is 0, so the graph would include that point. Kind of silly, but you could do that technically. That's a function defined everywhere, but it's not continuous at 0. The limit does not exist. There's a third way reasons it can happen, and this is the wildest of all, calling this a wild discontinuity. Here's a function that oscillates infinitely often in any little open interval containing x equals 0. It's this function right here. It's a piecewise defined function. F of x equals sine of 1 over x if x is non-zero, and 0 if x is 0. Now I'm going to show you the graph, but before we look at the graph, let's just think about it. I'm claiming this oscillates infinitely often in any little tiny open interval around 0, no matter how small it is. Why? Think about what happens as x gets close to 0. As x gets close to 0, 1 over x gets big. If x is 0.1, 1 over x is 10. If x is 0.01, then 1 over x is 100. If x is 0.001, then that 1 over x is 1,000. This 1 over x keeps getting bigger and bigger as x goes to 0. Sine of a number that keeps getting bigger and bigger, if you think about the graph of the sine function, oscillates in value between -1 and 1. There's your ordinary sine function. As the input x keeps getting bigger and bigger, you keep moving to the right, we're oscillating infinitely often. The input's just a plain x there. Back over here, it's a 1 over x. But those values still do keep getting bigger and bigger. Sine of them has to keep oscillating, and in fact, oscillating infinitely often. Here's a picture of the graph near 0. And now, of course, no computer could literally draw infinitely many oscillations. But it is drawing so many oscillations it helps you believe there's infinitely many of them. If you make an animation, you can believe it more. As you zoom in closer to 0, you can see it gets even denser. There literally are, for this function, infinitely many oscillations, no matter how close you are to 0. No matter how tiny your little interval around 0 is. That's a really wild discontinuity. I made the function defined at 0, but definitely the limit does not exist. Even the one-sided limits don't exist either, because the function output is not settling down on any particular number. Okay? I'm going to show you an example on Wednesday where something similar is going to seem to happen, and for another example. But in that other example, it's actually numerical error. This is not numerical error. This is really happening. How do you fix discontinuities? You have some homework problems like this. This is our last slide before the break. Sometimes discontinuities can be fixed by choosing parameters appropriately. I might put an exam question like this on Friday's exam. Take number 21 from section 1.7. It was one of your completion problems. This one right here. G of t is piecewise defined to be t plus k if t is less than or equal to 5, and kt if t is greater than 5. If t plus k aligned with a slope of 1 and a vertical intercept of k when t is less than or equal to 5, and k times t is a graph that goes to the origin. It's a direct proportionality with a slope of k, a little steeper here. But you only see that part of the graph once t is bigger than 5. Can you choose k to make these two pieces match up? Different k's give you different graphs, but look, there is one value of k where they match up. Right there. Right there. You can try to watch and see what k is when they match up. But it's easier to just do it algebraically. What do? Set the left and right hand limits equal to each other and solve for k. Okay, think carefully with me here. The limit of g of t as t approaches 5 from the left, that minus sign means from the left, can be computed using this formula because that's the formula in play when t is less than or equal to 5. So plug in t equals 5 into there and get 5 plus k. For any k, that will be its limit. Its left-hand limit. For the other one, we're letting t approach 5 from the right. We need to use the other formula because that's in play when t is bigger than 5. It doesn't matter that this is a strict inequality here, greater than as opposed to greater than or equal to. We still plug into this formula to figure out its limit to be 5k. Set these things equal to each other and solve for k, and k is 1.25. See, that seems right looking at the animation there. Watch the k when they match up. Does it seem to be about 1.25? It's hard to tell for sure, but it seems reasonable looking at those numbers. Zoom in if you need to there briefly. Looking at those numbers. Changing k shifts the first piece up because it's t plus k, that's a vertical shift. For the second piece, it's really a vertical stretch, k times t. And k is 1.25, they match up. Okay, let's take a break.